In this lecture, we will discuss about how to design 3-bit ripple counter or mod 8 ripple counter, and also we will see 4-bit ripple counter or mod 16 ripple counter. So, or simply we can say asynchronous counters. In the previous lecture, we discussed about 4 ripple counters, that is 2-bit up counter using negative edge triggered flip-flop, 2-bit down counter using negative edge triggered flip-flop, 2-bit up counter using positive edge triggered flip-flop, 2-bit down counter using positive edge triggered flip-flop. So we'll go very quick what we have discussed in the previous lecture. So this is the first one we have seen, that is 2-bit up counter using negative edge triggered JK flip-flop. See, that is first flip-flop output will drive the next flip-flop clock, which is negative edge, right? So it will do up counting. So this can be called as 2-bit up counter, or we can say mod 4 up counter, right? Or we can say divide by 4 counter. Yes or no? So see, if the first flip-flop Q0 is driving the next flip-flop clock and it is negative edge, so it will do the up counting. Second, we have seen negative edge triggered JK flip-flop, or we can say T flip-flop also. Here Q0 bar of the first flip-flop is driving the next flip-flop clock, so it will do down counting. So this can be called as 2-bit down counter, or we can say mod 4 down counter, or we can say divide by 4 down counter, etc. Right? And also we have seen 2 more circuits, that is positive edge trigger. So when Q0 bar of the first flip-flop is driving the next flip-flop clock and both flip-flops are positive edge triggered, then it will do up counting. So again it is 2-bit up counter or mod 4 up counter or divide by 4 up counter. And if first flip-flop Q0 is driving the next flip-flop and it is a positive edge trigger, it will do down counting. Again we can say 2-bit down counter, mod 4 down counter or divide by 4 down counter. So combinedly we can have like this. In conclusion, if the flip-flop is negative edge triggered and Q as clock, right, then we will get up counter. If negative edge trigger flip-flop but Q bar as clock, then we will get down counter. If positive edge trigger and Q as clock, we will get down counter. See, remember, if positive edge is there, then Q bar as clock, then we will get up counting, right? So this is briefly we can have like this. So keep in mind like this also. Or remember, we will not get question like this. So is it up counter or down counter, etc. So they will give some circuit. So we have to see either it is a mod 5 counter or mod 4 counter, right? By looking the circuit diagram, so we can easily identify it is a up counter or down counter. So if Q0 is driving the next flip-flop and it is a positive edge trigger, so what we will get? Down counting, right? If it is Q0 bar is driving the next flip-flop clock and it is a positive edge again, so we will get up counting, etc. Right? So this is our some brief what we have discussed in the previous lecture. Now we will see how to design this 3-bit ripple counters. The moment we said 3-bit ripple counter, or we can say mod 8 ripple counter, so how many states, possible states, first we will identify. So here n is equal to 3, right? So maximum count, capital N, will be 2 power 3, that is 8. So sequence will start from like this: 0002, then 001, then 010, then 011, then 100, 101, 110, then last state is 111, then it will come back to 000 again, right? So this is a binary sequence it will go. So how many? 8, but it will start from 0 and it will end with 2 power n minus 1, right? Now for n is equal to 3, how many flip-flops are the mod 8? So 8 is a count, so how many flip-flops required? 3 flip-flops required. So I have drawn the 3 flip-flops, and see, all are negative edge trigger flip-flops, right? And these flip-flops are T flip-flops. Instead of T flip-flops, I can use JK flip-flop also. So here all T flip-flop inputs will be 1 because it will be in toggling mode. Now can you identify, is it a down counter or up counter? See, Q0 is driving the next flip-flop. See, Q1 is driving the next flip-flop. So Q is driving the next flip-flop, and all flip-flops are negative edge trigger. So what we will get? We will get up counter, right? Now we'll see the operation using timing diagram first. Now, so this is the clock. So clock should have minimum 8 clock pulses, or it can go. So, and it is a negative edge, so I have denoted for negative edge trigger. Then Q0, Q1, Q2. Now if you see, the moment we have applied clock, the Q0 always change its state. And I remember I told you main clock is driving this LSB output. The last flip flop always MSB. That's why three flip flops means Q0, Q1, Q2 and so on. So Q0, Q1, Q2. Now first Q0 will change its state whenever clock negative edge comes. So we can easily draw the Q0 output. So always remember, all generally we will assume all are 0, 0, 0. So first we will draw Q0. So negative edge comes, so it will change its state. Then negative edge comes, change its state. Negative edge comes, change its state, and so on. So I can draw like this. Now we have to give negative edge for Q0 because Q0 will drive the next flip flop. So I can give negative edges like this, right? So this is negative edges are given. Now if you see flip flop 1 clock is coming from the Q0. So this is a negative edge, so I have given the negative edges for the Q0. Now whenever negative edge comes for the Q0, then only the Q1 will change. Now see, will it change here? No, because it is a positive transition, so it will be maintained that state only. But whenever negative edge come as Q0, then only it will change its state, and so on. See, negative edge coming, so previously it is 1, now it is changed to 0, and it will maintain that state. And whenever negative edge comes, then it will change its state, and so on. Negative edge come, it changes its state, and so on. So this is Q1. So Q1 is driving the next flip flop. So we have to give negative edge again here. Only 2 negative edges will get. So see here in the block diagram. So Q1 is driving the next flip flop, and it is negative edge. Now what we'll get? Up to this transition, whenever we get negative edge, then only we'll get this changes of state. So 0, now it getting to 1, and the next negative edge is coming here. So it will be maintained that state only. Whenever negative edge comes, then only it will change its state. Now if you see, this is 0, 0, this is 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. Next again we are getting 0, 0, 0. Now if you see like this, Q2, Q1, Q0. So Q2 is MSB, Q0 is LSB. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, then it come back to 0, 0 again. So how many states? Total 8 states. So 0 to 7. Now can we say what is the frequency division is happening? So 8 by 4 or 8 by 8 we will see. So this is if I take as one time period t, then if you see this Q0, so the time period will be 2t compared to clock. Now if I see this, the Q1, now this is the time period I can take, so this will be 4t. Then if I see this one, so from here, or if I start from here, see from here to here, 1, 2, 3, 4, 5, 6, 7, 8. So up to 8 it is not changing. So here, from here I will take, here to here there is a 8t compared to the clock. See, it is changing for every 2t, it is changing for every 4t, and it is changing for every 8t. So what can be the frequencies? This is F0. See, this is F by 2. This is F1, which is F by 4, and this is F2, F by 8. So what is the frequency division is happening? When we take output from the Q2, so we will get frequency division by 8. Now you can easily think, suppose this is second pulse, this is a minute pulse, this is hour pulse. So it will only respond for one time for 8 clock pulses. So now we can think how to design this watch, or we can say clock. So it depends on the main clock. So main clock will be generated somewhere, then we have to design different clocks. So f by 2, f by 4, f by 8. If you use 10 flip-flops, so what we will get? 2 power 10 is the state, so 1024. So it will divide f by 1024. If you are having 20 flip-flops, we will get f by 2 power 10 and so on, right? So that is how it is doing. So what is this counter now? We can give as, this is mod 8 counter because it is counting 8 states. So mod 8, we can say ripple counter, and what we are using is the up counting or down counting. So we can say ripple up counter using negative edge trigger T flip-flop, right? Now same thing, we can form a truth table, something like this. So initially Q2, Q1, Q0 will be 0. When we apply some clock, Q0 always it will change its state. So 0 to 1. Now 0 to 1 is a positive transition or negative transition? Positive. So it will not respond. If it is not responding, this also will be remaining its same state. Because 0 to 0, there is no transition at all. So it will be not affected. Next, second clock, it will be affected. So 1 to 0, there is a transition. So Q1 will affect. So it will change 0 to 1. So 0 to 1 positive transition. So it will not affect. So it will maintain that state only. Clock 3, it will change 0 to 1 positive transition. Will it change? No. So it will maintain the same state. If it is maintaining the same state, it will also maintain the same state because there is no transition at all, clock transition. Clock 4, it will change. So 1 to 0. So there is a negative transition. So it will also change. So this is 1 to 0. See, again it is negative transition. So Q2 also will be affected. So it will change from 0 to 1. Next, clock 5. So Q0 always changes. So 0 to 1. Positive transition. Will it change? No. It is not changing means it is not also change, or we can say it is not affected. So same change, same state. Next, 0 to 1. Then after one more clock, it will change it to 0. So 1 to 0, there is negative transition. So it will change its state. 0 to 1, positive transition. Will it change? No, it will not affect it. So 1. Next, last one. So it is changed to 0 to 1 when we apply clock. Then 0 to 1, positive transition. Will it change? No, same transition. It is not changing, so it will also not be affected. So same state I will get. Now when I apply clock 8, so this will change to 0. 1 to 0, negative transition. So it will affect. So again it will change it to 0. 1 to 0, negative transition. So it will also affect. So it will become as 0. Now we have started with 000, we ended with 000. If we apply one more clock, this will change it to 1. Positive transition, no change. This is also no change, and so on. Right? So 0, 1, 2, 3, next 4, next 5, next 6, 7, then it will come back to 0 again. So when we keep on applying a clock, it will rotate like this only, right? Now how many states is counting? 000 to 111, it is come back to 000 when we apply 8th clock. So it is counting either 8 clock pulses, or it is going through a sequence 0 to 7 and come back to 0 again, something like this, right? So this is mod 8 ripple counter, and it is doing the up counting. So we can make down counting also. So what is the change we have to make? Very simple. Just apply this Q0 bar to the clock of the next flip flop if it is a negative edge trigger. If it is a positive edge trigger, we have to do opposite way, right? So that we can do. So you try to do on your own 3-bit up counter using positive edge triggered flip flop. Okay. Next we will see mod 16 ripple counter using positive edge triggered flip flop. Now mod 16 means, or we can say it is 4-bit ripple counter. So if it is a 4-bit ripple counter or mod 16, so how many states will be there? 16 states. So for 16 states, how many flip flops required? So that we can now calculate like this. So 16 means n is equal to 16. So how can I make in powers of 2 power 4? So how many flip flops required? 4 flip flops required. So I have drawn 4 flip flops, and all flip flops are T flip flops only. I can draw using JK flip flop also. And if you see, all flip flops are positive edge triggers. If there is no bubble, it is a positive edge triggered flip flop. And if you see, Q0 is driving flip flop 1, Q1 is driving flip flop 2, Q2 is driving flip flop 3. That is, Q is driving the flip flop clocks. That is, what is the counter? Up counter or down counter. So if you remember that note points, if you see this here, positive edge triggered flip flop and Q as clock. So what is this? Down counter. If you remember that 4 points, or you can easily remember, Q0 is driving the clock and it is a positive edge, so it will do down counting. So it is a down counter. So that way anyway we'll verify using the truth table. Right? Now we'll see the operation. So initially there is no clock, so all I'm assuming is 4 zeros. Now the moment we apply clock 1, so it is a positive edge trigger, then what will happen? Q0 always change its state. So Q0 is changing from 0 to 1. Is it a positive transition or negative transition? Positive transition. So Q0 is applied to the clock of the flip flop 1. So what is the flip flop 1? So it is changed. So it will also change to 1. Again it is a positive transition. So Q1 is driving Q2. Again it will change. So Q2 is driving Q3. So it is also changes its state. So what is this state? So what is this state? State 15. Yes or no? If I convert these 4 ones into decimal, I will get this as 15. So from initial state 0 to directly it is jumped to 15. Right? So it will do down counting. Now if I apply one more clock, so what will happen? Q0 will change its state from 1 to 0. So 1 to 0, it is a negative transition. So this will not affected, this will not affected, and so on. If this is not affected, so there is no transition. So it will not be affected, and so on. And remember, always the main clock will be driven the flip flop 0, or we can say LSB, and the last flip flop will give MSB. So Q3, Q2, Q1, Q0. That's why I have written Q3, Q2, Q1, Q0. Now second clock, if I apply, the Q0 will change its state. So 1 to 0. Now 1 to 0 is negative transition. So these 3 will not affected. I have written like this. Now when I apply one more clock, so the Q0 will change its state. So what is this? 0 to 1, positive transition. So it will change its state. 1 to 0. What is this? Negative transition. So it will not be affected. It will also not affected. Next, clock 4, positive transition. So 1 to 0, it is negative transition. Any change? No. So it will be as it is. If it is not transition, if there is no transition, Q2, Q3 will not be affected. Next, clock 5. So 0 to 1, positive transition. So it will change. So 0 to 1, positive transition. So will it change? Yes. So it will change it to 1 to 0. 1 to 0 is negative transition. So Q3 will not be affected. And so on. We can fill this table. So you can verify. So just to pause the video, you try on your own. So one more clock, it will change. 1 to 0, negative transitions, no change. Here also no change. Here also no change. One more clock, so it will change. Positive transition. So yes, Q1 will change. 1 to 0, negative transition, no change. So 0, 1. This is. So can I write the sequence? This is 14, 13, 12, 11, 10. This is 9. Next, if I apply one more clock, 8. So the Q0, previously it was 1, now it will change it to 0. 1 to 0, negative transition. So it will not change. So this is 0, this is 0, this is 1. What is the state? 8. Next, one more clock. So it will change it to 0 to 1. So positive transition. So it will change. 0 to 1, positive transition. So this is also will change. I'll get 1. So 0 to 1, positive transition. So it will it change? Yes. So it will make 0. So what is this? 7. Now one more clock, it will change. 1 to 0, negative transition, no change, no change, no change. So what is this? 6. 11, one more clock, 0 to 1, positive transition. So it will change? Yes. 0. 1 to 0, negative transition, no change, no change. There no transition is happening, so it will not affect it. Next, what is this? 5. One more clock. So will it change? Yes. 1 to 0. It is negative transition, no change. So it will not no change. What is this? 1. No change. What is this? 4. One more clock, change, positive transition. So will it change? Yes. Positive transition. Will it change? Yes. Here negative transition. Will it change? No, not affected. So 0. What is this? 3. One more clock, change. 1 to 0, negative transition. So no change. No change means again I will get no change here also. So this is what? 2. Next, 15. So 0 to 1, positive transition. Will it change? Yes. So it will change to 1 to 0. Negative transition, not affected. So what is this? 1. One more clock, 1 to 0. 1 to 0 is negative transition, so these 3 will not change. What is this? 0. Now if I give one more clock, what will happen? It will change it to 1. So 0 to 1 positive transition. So will it change? Yes. 0 to 1 positive transition. Will it change? Yes. Again 0 to 1 positive transition, so it will also change. Again it is changed to 15 and so on. Right? So this is the how many states is counting? 15 to 0 back. So total 16 count. So I can say this is mod 16 counter. Now can you tell what is the frequency division will happen? If I take output at Q3, so I will get this F3 will be F by 16. Right? That is after 16 clock pulses, the Q3 will change its state again. Right? That's why it will do mod 16 counter, or we can say F by 16 frequency division will happen. Right? So this is about the mod 16 ripple counter, or we can say 4-bit ripple counter, or divide by 16 ripple counter. Now what is the type of sequence? It will do down counting. So the name will be given like this: mod 16 ripple down counter using positive edge trigger T flip-flop. Now can we make up counting? Yes. So only change will be Q0 bar will drive the clock of the flip-flop 1. Q1 bar will drive the clock of flip-flop 2. Q2 bar will drive the clock of flip-flop 3. Right? That you can make easily, and you can verify the truth table also. Right? So I will see. I'll just show the diagrams. Just go through it. So this is 3-bit down counter using negative edge triggered T flip-flop. We have seen 3-bit up counter. Now this is the circuit diagram for down counter. So what is the correction or connection we have made is Q0 bar is driving the next flip-flop, Q1 bar is driving the next flip-flop, and it is negative edge trigger. So we'll get down counting. Right? If you remember that 4 points, so we can easily identify it will do the down counter. Similarly, this is 4-bit up counter using positive edge trigger T flip-flop. I did not mention it is ripple counter. So by default these are ripple counters because the first flip-flop output is driving the next flip-flop clock. That's it. Simply it is ripple counter only. So this is 4-bit up counter. See here, this is a positive edge trigger, but Q0 bar is driving the next flip-flop. Q1 bar is driving the flip-flop 2. Q2 bar is driving the flip-flop 3. And what is this flip-flop? Or we can get LSB. Q0 is LSB and Q3 is MSB. Right? So the last flip-flop always give the output of MSB. The first flip-flop will give the output of LSB. Right? You can verify the truth table. If you are having any doubt, please post a comment. Right? In the next lecture, we will see how to design mod 6 counter or how to design mod 10 counter. That is, we need to stop the sequence in between. That is, if I take this counter, so it will do the down counting. So it will start from 7, 6, 5, 4, 3, 2, 1 and come back to 0 and come back to 7 again. Yes or no? 1 to 0, come back to 7 again, and it will do like this only. Suppose it started from 7, 6, 5, 4, 3. Suppose if I have to come back to 7 again, right? I have to skip 2 and 1, 0. I have to skip these 3 states and come back to 7 again. And if I would doing the up counting, so 0, 1, 2, 3, 4, 5. Then after this 5, I have to come back to 0 again. So we are counting how many states? 1, 2, 3, 4, 5, 6. So it is nothing but mod 6 counter, and it is doing the up counting. So mod 6 up counter. If I take the 4 flip-flop one, so I can make mod 10 counter or mod 11 counter or mod 12 counter, etc. So we can stop in between. So how to design those type of counters, right? That we'll see in the next lecture.